This video involves solving equations which have logs and exponentials as part of those equations. We're just going to simply look at a couple of examples of the different types of questions you might see. And to solve these, we're going to use the information that we learned in the previous slide, which shows us that if we take the natural log of an exponential function, we can eliminate the exponential part, or if we take the exponential of a natural log, we can eliminate the log part. So let's look at example 1. We have solve e to the x equal to 9. So we have an exponential function on its own on the left hand side. To remove that exponential, we take the natural log. So we would write ln e to the x equal to ln 9. The ln e is removed, so now we are left with x is equal to ln 9, which we could put into the calculator, and we get a value of 2.197. Watch your rounding on that again. Make sure you round correctly to the right number of decimal places and that the rounding is correct in terms of greater than 5, equal to 5, or less than 5. Example 2. Solve ln x equal to 5. This time we want to remove the natural log, so we take the exponential of both sides. So that would be e to the ln x equal to e to the 5, leaving only x on the left hand side and e to the 5 on the right hand side. When we evaluate e to the 5 in the calculator, we get 148.413. Now we'll look at a few trickier formulas. Example 3. Solve 5e to the power 2x plus 1 equal to 12. So our power this time is an expression of 2x plus 1. The first thing we need to do is divide by 5. So we would be left with e to the 2x plus 1 equal to 12 divided by 5. So we've isolated the exponential function. And 12 divided by 5 is 2.4. So we can rewrite that. Now we want to take the natural log of both sides. So ln e to the 2x plus 1 and ln 2.4. On the left hand side, that leaves us with 2x plus 1, and we've got ln 2.4 on the right hand side, which we can evaluate. So we've got 2x plus 1 is equal to 0.875. And we'll continue on the next slide by transposing the left hand side, so taking away 1 and then dividing by 2. So we had 2x plus 1 equal to 0.875. So if we take away 1, we're left with minus 0.125. And if we divide by 2, we're left with minus 0.0625. Right, next example. Example 4. 4 ln 3t plus 5 equal to 10, and we're trying to solve that. Okay, so divide by 4 would be our first step. That's us isolated our log on the left hand side, and we have 4 divided by 10 on the right hand side, which is 2.5, so I can write that as the next step. Now that we have the natural log on the left hand side, we can take the exponential of those both sides. So that's e to the power ln of 3t plus 5 equal to e to the power 2.5. The e and the ln will cancel out, so we'll have 3t plus 5 and e to the power 2.5 is equal to 12.182. And finally we can transpose for t, so 3t will be equal to, take away 5, so that would be 7.182. And then finally divide by 3, so t is equal to 2.394. Right, example 5. An initial current of I0, which is in amps, falls to I in amps after t seconds. And the formula would be I is equal to I0 times e to the power negative kt. We're asked to do two things. We're asked to find k to two decimal places, given that we have a time of 0.02 seconds, and an initial current of 150 amps, and that falls to 90 amps. Part B is then asking us to find the time that it takes for the current to fall by half of its initial value. So we'll start with A, so the solution to A. First of all, we want to know what information we've been given. So we've been given the initial current, which was I0, and that's 150. And we were given the current that falls to, which is I, so that's 90. And we're told the time, t, which is 0.02. So we can sub those all into the formula that we're given, and the only thing that we won't have a value for would be k, and then we're going to solve for k. And we're going to need to transpose and take the logs to be able to find k. So we'll do that on the next slide. So we had I equal to I0 times e to the minus kt. I was 90, so we have 90 is equal to I0, which was 150, times e to the minus k times t, which was 0.02. Now I'm just going to swap sides here, so I've got 150e to the negative 0.02k equal to 90. Now at this stage we have to transpose, so we divide by 150. So the exponentials left on that side, and we have 90 divided by 150. So that's e to the minus 0.02k is equal to 0.6. And now we have an exponential function on the left hand side, so we will take the natural log to be able to eliminate that. So it's the natural log of both sides, which will leave us with negative 0.02k equal to, that should be ln, equal to ln 0.6. The final step then to find the value for k will be to divide by negative 0.02, which we'll do on the next slide. We will have k equal to ln 0.6 divided by minus 0.02, so k is equal to 25.54 to two decimal places. That's what it asked us to round to in part A. Now just before we move to part B, we can now rewrite our equation, but instead of having k, we can have 25.52. So it will be I is equal to I0 times e to the negative 25.54t. And we will use this formula here in part B. So part B talks about the initial value falling to half. So the current falling from the original value down to half of its value. So that would suggest that if we thought about a ratio of I over I0, then we'd have 1 over 2. So that shows you that the ratio of these two values, the current and then the initial current, when we divide them, they want to be a half. So the initial current is 2 times bigger than what you're left with after the specific time that we're interested in. So basically, when we start with our equation that we just wrote at the end of part A, so that was e to the so it was minus 2.25.52t, we divide by I0 to leave us the exponential function. And we have just said that this part here, the ratio of the current divided by the initial current must be a half, because that's what we're interested in it falling by. So we can write e to the minus 25.54t is equal to a half. And again, we have to take the natural logs to be able to continue on and solve this. So we'll do that in the next slide. So we have ln e to the minus 25.54t equal to ln a half, or you could be writing 0.5 there. That will leave us on the left hand side with 25.54t equal to ln a half. And finally t must be equal to ln a half divided by minus 25.54. When you work that all out, we find that the time is 0.027 seconds. So it takes the current 0.027 seconds to drop from its initial value to half the value. Right, the final exercise has a graph and it asks us basically to find out the equation of that graph. So the graph has equation y is equal to e to the power kx and passes through the point 2, 20.09. They want us to find k and then write the equation of the function. So we have an unknown k and we're trying to find that out. So this takes us back to the earlier graphs that we did for exponential and log functions, where we were trying to find an unknown value and we were subbing in the point. So we're going to do the same here. So first of all, write the equation. Here's our point, so this must be x and this must be y. So if we put 20.09 here, and we can have e to the k times 2 there. First of all, I'm going to swap sides, so I'm going to have e to the 2k equal to 20.09. And then we have to take the natural logs of both sides again to be able to eliminate e. So ln e to the 2k is equal to ln 20.09. So 2k will be equal to ln 20.09. And finally, k will be ln 20.09 divided by 2. I've not got a lot of room here to fit that in, so I'm just going to write down what that answer is. That will be 1.5. So k is 1.5. And then if we want to write the equation will be y is equal to e to the 1.5x. And that is us completed the exercises.